Spherical coordinates are much more difficult to work with than cylindrical coordinates. In this case, all three variables from rectangular coordinates are interacting with each other. Here is the graph of the point x, y, z in rectangular coordinates. We want to get from this to spherical coordinates. Rho is the distance from the point to the origin. We can get this value using the distance formula. Theta is the same angle that we used in polar coordinates. To get this, we need to look at the image of the point when staring down the z-axis. Another way of saying this is that theta is the angle that we get in polar coordinates if we project the point onto the xy plane. Phi is the angle that is made with the positive z-axis when the point is connected to the origin. This is called the azimuthal angle and is somewhat analogous to lines of latitude on a globe, except that the reference is the North Pole and not the equator. From this diagram, we have the ability to calculate how to get back to rectangular coordinates from spherical coordinates. A trick that helps most students to see this is to use alternate interior angles and draw the angle phi at the point xyz. This helps to relate the sides of the triangles more naturally to the sides of the box. We can see that z is the side adjacent to the angle phi, and that the hypotenuse of the triangle in the xy plane is the side opposite the angle phi. Everything else is just right triangle trigonometry. You should really try to reconstruct this picture on your own from scratch. That is a good measure for how comfortable you are with the coordinate system, and the practice of it really helps to get these relationships to sink in. A good way to build intuition with spherical coordinates is to think about the shapes you get when you hold one or another variable to be constant. If rho is constant, you just get a sphere. This is because rho is the distance from the origin, and saying that this value is a constant is exactly the definition of a sphere. If you hold theta constant, you get a vertical half-plane coming out from the z-axis. It's important that you only get a half-plane and not a full plane. This is related to phi only being measured from the positive z-axis and not all the way around. Lastly, if you take phi to be a constant, you get a cone. As phi gets larger, the cone opens more widely. When phi equals pi over 2, you actually just get the xy plane. And then larger values of phi give you a cone in the negative z direction. You should try to visualize what curves you get when you hold two of the variables to be constant. If you can do that, then you should have a good understanding of how the spherical coordinate system works. Activity 11.8.6 walks you through the derivation of the volume element in spherical coordinates. We're going to leave it as an activity instead of working through it because it's a good culminating challenge as we approach the end of the book. The basic idea is that we're approximating the volume with a box, and you need to think about the lengths of the three dimensions. Everything else is just figuring out how to approximate those values. The end result is that dv is equal to rho squared sine phi d rho d theta d phi. Even if you don't fully understand the derivation of the volume element, once you have it, you should know what you need to do with it. We can just make the substitutions from rectangular to spherical coordinates and plug in the volume element to get the triple integral for spherical coordinates. The formula looks long, but that's because it explicitly contains all of the substitutions. The good news is that setting up the integral is exactly the same as before. You are looking at trying to set up a sequence of lower to upper regions that map out the final shape. The diagrams we created earlier can be extended to help think about lower to upper shapes. For rho, you get a spherical shell. For theta, you get a wedge-shaped region, sort of like a slice of a tall circular cake. And for phi, you get a conical shell, somewhat like an ice cream cone. This is probably the most difficult visualization sections for the book. You don't have a lot of experience to help you see these shapes, and so it's going to be tough. When trying to think through the regions, it's okay to sketch multiple pictures to try to get it right. You shouldn't imagine that you'll draw it right the first time all the time. But as you keep working through the problems, you should start to get a little bit more comfortable with this. Just take your time with these problems, and you should be able to make it through.